Hi. Today we will start a new topic, which is electric current. But first, before we discuss this topic, I would like to solve just one more problem from electrostatics, so that you get feeling how to solve more complicated problems in electrostatics. So let's be a ball of conducting material of radius r1 and another ball of radius r2, such that the distance between these two balls, the distance between their centers, is d. And these two balls are connected to a source of voltage, to external battery, which has electromotive force. Well, let it be U. So U is the voltage on the terminals of this battery, on the external two external contacts. And the question is, what charge will be accumulated on each of these balls? So if we have here a plus terminal and minus terminal of the battery, well, it means that the some plus Q, the charge will be accumulated on the left ball, and some minus Q will be accumulated on the right ball. Because the battery will take some number of electrons, actually a huge number of electrons from this ball, and carry these electrons to another sphere, and so that if the charge on the left ball is plus Q, then the charge on the right ball will be minus Q. The charges are equal in magnitude, but opposite in sign. So we have to find this Q, what charge will be carried by each of these balls, if we know the radii of the balls and the distance between them. So how can this problem be solved? We must remember everything that we know about the electrostatics, and we know if the sphere is charged, then this sphere will have some potential, some electric potential. Let it be Phi1, which is defined by a well-known formula that we have already discussed, which is Q over R1, and K is the constant. You know what is K is 9 times 10 to the 9th power in international system of units. And this potential is positive because the charge is positive here on this sphere. But here the potential, electric potential on the second sphere will be negative because the charge here is negative. And so it will be minus KQR2. And also we know that the external battery, external source of voltage, creates potential difference between these two spheres equal to U. So potential difference Phi1 minus Phi2 must be equal to the voltage of external source. Substituting these expressions here and also this expression here, we obtain K and Q will be the common coefficient. So we take K and Q out of the round brackets, and what will be here? 1 over R1 minus, and another minus will give us plus 1 over R2, and that must be equal to external battery voltage. And so from this equation we can easily find this charge the charge Q, which will be accumulated, plus Q on one of the balls and minus Q on another ball. And this Q will be given by, if we divide U by these round brackets, first we have to divide by coefficient K, and then by this round bracket. So that will be the answer to the problem. We can certainly write this answer in a more suitable way, which will be U R1 R2 K divided by R1 plus R2. That will be the answer to the given problem. That will be the charge accumulated on each of the spherical conductors. So whenever you solve a problem in electrostatics, you must recall all the formulas which you know from electrostatics and all the facts and ideas, because in different problems you have to apply, you have to use different ideas and different formulas. And now we go to our new topic, which I declared was electric current. What is electric current? It's a directed movement of electric charges. So we have suppose we have a conductor, a conducting material, and there are some charges. In general case, there are both positively charged particles and negatively charged particles. In general case, we have both types of charges. If the charges move somehow, if they have directed motion, then this is not the static equilibrium. This is not the state of static equilibrium. In static equilibrium, charges don't move, don't have a certain directed direction of motion. In static equilibrium, that is in electrostatics, the potential difference between two different points, between these 2 points A and B, the potential difference, potential A minus potential B, will be 0 in electrostatics. In electrostatics, between a potential difference between any 2 points of the conductor will be 0, and that is the condition of static equilibrium of all the charges. If you have some directed motion of charges, then the potential difference is not 0. It must be something like some different, it must have some different value. If the potential difference is not 0, if there is some external voltage on the conductor, then the charges will move. For example, if you have a plus potential here and minus potential here, then the positively charged particles will move to the minus and negatively charged particles will move to the plus, to the positive potential. I told you that in general case we have both types of electric conductors, both positive and negative. For some years in the beginning of the 20th century, people thought that in metals we have only negatively charged particles, that is electrons, which move and make current in metals. And then later it turned out that in some metals there are also positively charged carriers of current, positively charged carriers in metals and semiconductors are called holes. So practically always you have some portion of holes and some portion of electrons, and both charges of both signs make their contribution to electric current. If it's not a metal but a semiconductor, then there are n-types semiconductors, n-type semiconductors which have negative charges as the carriers of the current, and also we have positive type semiconductors where positively charged holes make the largest contribution into the electric current. But there are other situations. For example, if we have an electrolyte solution, for example, a solution of some salt or some acid, then in electrolyte solution, every molecule of salt or acid is dissociated into two ions. Not every, but most of molecules are associated into two ions. One ion is positively charged and another one is negatively charged electron. And so in electrolytes, we have equal numbers of positively and negatively charged carriers of electric current. The same thing happens in gas discharge. In a gas discharge, like in a gas laser, the electric current goes through the gas, and there is the process of ionization of gas. And in this case, we have both positively charged ions in gas and negatively charged ions, either free electrons or electrons attached to some molecule which becomes negatively charged ion. So in many practical cases, we have both positive charges and negative charges, and both types of charges make their contribution to electric current. So when people thought about what is the direction of current, it was agreed by convention that the direction of current should coincide with the direction of motion of positively charged particles. So in this particular case, the direction of electric current will be this one, from A to B. The direction of electric current is always assumed to be the direction of positively charged particles. No matter what type of conductivity you have in a certain case. The current is always goes from positive to negative electric potential. So in order to have current, we must apply some external potential. The simplest case is when you have a charged capacitor, and we attach some external circuit to this capacitor. This is a switch, and this is some external resistor. The switch may be closed or may be open. If the switch is open, it means that the wire is broken and no current can flow through this wire. If we close the switch, then there is a contact and the wire becomes a continuous conductor, and the current may flow through this wire. And we know that the current will flow from positive potential to negative potential. So the current here will flow in this direction. What will happen if we close the key? Then the charges will flow and the capacitor will discharge. It means that the amount of charges on both plates will decrease, and will decrease until the potential difference is zero. The current will flow until the potential difference is zero. And if the capacitor is not very large and the resistor is not very large, then this will happen very quickly, just in some portions of a second. The potential difference will decrease from initial potential difference to zero, and the current will stop. It will cease to exist. So in order to sustain the current, in order to arrange for a constant current, we must somehow invent a mechanism to take negative charges from the lower plate of this capacitor and move them to the upper plate. This will be, if we talk about electrons, then electrons will go in different directions. So we have to take electrons from the upper plate and move them against the field to the lower plate. In order to sustain the potential difference, some electrons will go from the lower plate to the upper plate. The direction of electric current is different by convention, but it makes no difference. You may think of some positively charged particles moving along the conductor, or you may think about electrons moving in opposite direction. It makes no difference. The result will be the same. Whatever charge you may, whatever kind of charges you may assume, the result will be the same, the final result. So actually, if electrons initially flow from the negatively charged plate through this external circuit to the positively charged plate, because electrons are attracted to the positive charges or repelled from from one another. There are many electrons here, and they are repelled from one another, and they go to positively charged. Then we have to take them in order, if we want to sustain the potential difference, if we want to keep it constant, then we have to take electrons from the upper plate and move them to the lower plate. And while moving the electrons, we will move them from positively charged plate, where the electrons are attracted, to negatively charged plate, where the electrons are repelled from it. So we will have to apply some force, external force, to each electron. And that is the only possible way to keep the potential difference constant. We have to apply some constant force and take the charges from one plate to another. And this external force is actually, it's arranged, it may be arranged in different ways, in different sources of potential and different sources of voltage. This external force may be arranged either as a result of chemical reaction or as a result of the action of Lorentz force, as in electric generators, where a rotor with many wires wound on it is rotating in magnetic field, and so the wire goes through the magnetic field lines, and there is a the Lorentz force acting on each charge carrier. And so this is the external force that acts on each charge carrier and moves it in the direction opposite to the electrostatic forces. So on each charge, an electrostatic force will act. That is electrostatic force, and that is an external force. An external force is acting against the electrostatic forces. Such is the general idea, which is behind the processes that go on in any voltage source, in any battery, be it a chemical battery or in any electric generator. An external force must take charges and move them against the forces of electrostatic attraction. So such an element of such a source of voltage is usually denoted by such a symbol. Well, it means the cell where some external forces move charges in the direction opposite to electrostatic forces. Some external forces perform work, and due to this work, the current may flow through the outside circuit, and due to this work performed in the source of electric voltage, the current may perform work somewhere in the external sources. The current may rotate electric engines, or may cause some chemical reactions, or may heat some conductors, etc., etc. So what actually are the manifestations of electric current? Suppose we have electric current, constant current created by some external source. Any external source produces some potential difference. Any external source of voltage is characterized by some voltage on its terminals, on its end contacts. So this voltage is usually denoted by something like E. This is E, and it's called electromotive force and it's denoted by such a abbreviation, electromotive force, EMF. Electromotive force. External, that is the external force which moves, actually the external force which moves the charges. But this force is measured in volts, and the EMF, electromotive force of any charge, of any voltage battery, of any voltage source, is measured in volts because it produces some potential difference. So if the current flows through external circuit, what may be the manifestations of current? How does this current act on the circuit through which it flows? So there are many possible manifestations of current. First, heating of external conductors. That is heating. Second, if the heating is too strong, if it's too large, then the temperature of external conductor will grow to high values like 1,000 and more than 1,000 degrees Celsius. And in this case, the conductor will not only be heated, but it will glow. It will produce light, like a filament in an electric bulb. So this may be a glow producing light, illuminating like an electric bulb does when its filament is heated up to high temperature and is radiating light. And we use this phenomenon in electric illumination. So another possible manifestation of current, it may be not only heating or radiation of light, it may be some chemical reactions. Some chemical reactions may go due to chemical reactions may originate because of the electric current goes through the electrolyte solution, for example. Another manifestation of electric current is its magnetic action. If you take a magnetic needle of a compass, for example, then it will react to the current because the current in a wire produces magnetic field. We will discuss this phenomenon in greater detail later. So, but one of the manifestations of current is a creation of magnetic field around the conductor. And also, if the current goes through a gas, for example, through some gas volume, then the current may ionize the gas and there will be a gas discharge. And again, it will be accompanied by heating of gas volume and glowing of this electric discharge, which will radiate light, like in lasers, like in modern lamps, daylight lamps, where the gas discharge is glowing to illuminate the room. So this may be a creation of the electric current will create a gas discharge, and in many cases gas discharge is used to illuminate houses and to illuminate streets and rooms. So there are many manifestations, possible manifestations of electric current. It's a complicated phenomenon which manifests itself in many different ways. So the science that studies the electric currents is actually all the electromagnetism, electric radio engineering. This is a huge science which actually studies direct current and alternating currents. All the electric engineering studies this phenomena. So this time it's necessary to say that if we have some potential difference on the voltage source, then the electric current flows in the outside circuit, and the potential difference along the wire is assumed to be zero because wires are always produced, in most cases are produced of such material which possesses good conductivity, so that the potential difference on the wire is zero. But there are some elements which are called resistors, and they are resisting the flow of electric current, and so all the potential difference will fall on resistors rather than on wires. So the potential difference on this resistor will be the same as on the battery if the internal resistance of the battery is zero. We will talk about it, about the internal resistance of batteries. So the potential difference here in general case, but if the battery has some internal resistance, then in general case some voltage will fall on this internal resistance, and the voltage on the outside circuit will be smaller than the voltage than the EMF. So in general case, the potential difference in the outside circuit is smaller or equal to the electromotive force. That is, the voltage of the battery in general case is larger than the potential difference of voltage in the outside circuits if the battery has some internal resistance. That's actually always the case, that the battery has some small internal resistance. So in general case, the potential difference on the outside resistor is smaller than the electromotive force of the battery. But anyway, if there is some potential difference on the resistor, then the current strength will be directly proportional to the potential difference on this element and inversely proportional to the resistance. And this is the Ohm's law, which was established experimentally. Ohm's law. It was established experimentally in many experiments, and it works well for constant resistors. It should be said immediately that the Ohm's law is not always applicable. Sometimes this law cannot be applied in some cases. In some cases, there are some elements in radio electronics which do not obey this law. And these elements, well, we will discuss it a little bit later. But now it's the right time to say that the potential difference is measured in volts. I told you about it. And the resistance is measured in ohms. To use this surname of this physicist who discovered experimentally this law. And the current strength is measured in amperes, again, in honor of the scientist named Ampere, Charles Ampere. So in the international system, this is the basic unit. The ampere can be measured by its magnetic interaction of wires, and the voltage is defined as the work that should be produced to move unit charge. If the work equals 1 joule to move a unit charge from one point to another point, then the potential difference between these 2 points is 1 volt. And hence the what is 1 ohm? It's from this equation, it's 1 volt divided by 1 ampere. That is the definition, actually the definition of 1 ohm resistance. So the next thing which is important to discuss is exactly the internal resistance of a battery, of a voltage source. So let's consider this situation when we have some external voltage source and there is an internal resistance of this battery, which I will denote as small r. And we have such closed circle and closed circuit with internal resistance of this battery. The battery has electromotive force E and internal resistance. So this is a single device, and these 2 points are external contacts or external terminals of the battery. And this is the external circuit, and the current will flow in this direction. And so we can write for this circuit that the potential difference on the external resistance, potential difference here between these 2 points, will be the current strength, or the strength of electric current times resistance, and also the potential difference on this internal resistance of battery will also be defined by the Ohm's law. It will be the current, and the current is the same in any point of such a closed circuit, the same current times the small resistance of the battery. You know that the potential difference is defined through a work which is needed to carry a charge. So let's suppose that some small charge, delta Q, goes around this circuit, and when it returns to the same point, the total work produced by electrical forces must be the total potential difference. The potential of this point does not depend on whether we move from this point to the external circuit or whether we return from the external circuit to this point. The potential must be the same. So the potential difference, if we count the potential difference from this point, here it will be U, which according to the Ohm's law is proportional to the current and the resistance. And then it will be, the potential difference will be delta P, the potential difference on the internal resistance. And then we must take into account the potential difference on this battery, on this voltage source. It has a potential E here, and if we go from higher potential at this point to lower potential at this point, and from higher potential here to lower potential here, then when we go through the battery, we will go in the opposite direction, from lower potential to higher potential. So here we will have minus with a sign minus equal to 0. And substituting all these expressions from the Ohm's law, here, we will obtain the first term will be ER, the second term will be E small r, and all this is equal to electromotive force. So this is the electromotive force of the battery. Yes, and this is the voltage on the external resistance. And so the voltage on the external resistance may be obtained from here as an electromotive force minus E times small r, which is the external resistance. That's why I told you that the voltage on external resistor is smaller or equal to E, because always when we measure the voltage on external resistance, this quantity, we take the electromotive force and subtract something from it. So U is always smaller than electromotive force. But U will equal the electromotive force if the current in this circuit is 0. So if the current is 0, then the voltage on external terminals of the battery will be exactly equal to the electromotive force of the battery. How can we achieve this condition that current is 0? We must break this wire. We must somehow open the key here, not to allow the current flow. And so in this case, if we open the key, the current will be 0. The current cannot, the electrons cannot jump through this separation of contacts. And so the current will be 0. And only in this case, when the current is 0, then the potential difference here will be equal to the electromotive force of the battery. If we close the key and allow the current to flow, then the flowing current will arrange for some potential difference fall on the internal resistance of the battery. And in this case, the voltage on the external terminals of the battery will be smaller than the electromotive force of the battery. That's all there is to say about the internal resistance of the battery and what is the role of this internal resistance, and how can we measure the voltage on, how can we measure the electromotive force. In order to measure the electromotive force of the battery, we have to carry out measurement when the current is 0. And now I would like to talk about one important issue, a small and very easy problem, very simple, very easy to solve, very simple problem. Suppose the internal resistance of a human body is about 20 kiloohms, which is close to reality. And this person, suppose this person has touched a cable which is at the voltage 220 volts, which is the standard voltage in electrical circuits and electrical power circuits in the buildings in this country. So this is the standard voltage for electric cables inside the building. And this is something close to the internal resistance of a human body. What current will flow through the body of such a person who touched the naked wire which is under the voltage? So the current can easily be calculated from the Ohm's law. It should be proportional to the voltage and inversely proportional to the resistance. And that will be 220 volts divided by, well, something like I told you, something like 20 kilovolts, which means kilo ohm, which means 20,000 ohms. And that will give you approximately 220 divided by 20. Well, it's about, well, it's exactly 11, and that will be 10 to minus 3 power, and the result must be obtained in amperes. So that will be approximately 11 milliamperes. Such a current will flow through a body of a person who touched electric cable which is under the voltage of 220 volts. This seems to be a small current, just a few millivolts, but it should be said here that experimentally it's known that if a current flowing through a person is larger or about 15 milliamperes, then the person is unable to release the grip on the electric cable. If you touch the electric cable and such current about 15 milliamperes flows through a body, then the muscles become so stiff that you are unable to release this grip and to throw away this cable. You are unable. You will be attached to this grip, to this wire, and you will be unable to extricate yourself and to release yourself from this voltage. And this may happen. This may have very bad consequences for your health, up to a death of a person, up to a stop of heartbeats. So anything may happen if the current is this one. But if the current is slightly smaller, then the person is usually able to release by himself. So the current strongly depends on the resistance of the body, because the voltage is always constant, 220 volts. But the resistance of human body depends strongly on many conditions. First of all, the atmospheric conditions and weather conditions. If there is a high humidity, then the resistance is much smaller. The resistance of human body depends on humidity in the air, that is, on weather conditions. And you cannot predict what weather conditions will be tomorrow or even in a few hours. So, and you don't even pay attention to weather conditions every moment of your life. So the resistance of human body may turn out to be smaller, and then the current will be higher. It will be larger. Also, the resistance of human body depends strongly on your health condition. If a person is a little bit sick, then the resistance of his body is reduced. If a person also has, the resistance depends on the soles of your shoes that you wear and on the floor on which you stand. If you stand on a specially designed rugged rubber mat, then the overall resistance will be high and the current will be very small, and that will be not very dangerous. But if there is no special rubber mat under your feet, then the resistance may be very small due to the material of the floor. And then again, the current will be much higher than that and even higher than that. So when somebody tells you, oh, I touched 220 volts, nothing really happened, it's nothing, it's all, don't care about it, it's not dangerous. If somebody tells you about this, don't believe him, because sometimes it's not dangerous, but sometimes it's very dangerous when you will be unable to release the grip on the wire under voltage. So that is a simple demonstration of Ohm's law calculations. And the next topic will be a series and parallel connection of resistors. A serial and parallel connection of resistors. So if we have some resistors R1, R2, and etc. There may be many resistors, and all of them are connected to some voltage source, so that the current may flow in this direction from plus to minus what will be the resistance of this circuit, the resistance between points A and B. So according to general Ohm's law, the resistance between points A and B is directly proportional to the potential difference between these 2 points and inversely proportional to the current, according to the Ohm's law. And the potential difference between points A and B is equal to the potential difference on the first resistor plus the potential difference on the second resistor, because the potential difference is defined through the work produced on moving some charge and the work which is produced when you move the charge from this point to this point, and then the work produced to move from this point further to this point B, or this total work will be just equal to the work which you produce when you move the charge from point A to point B. So based on the definition of potential difference, we may assume and we may be sure that the total potential difference between points A and B will be equal to the potential difference on the first resistor plus the potential difference on the second resistor. That is from the definition of potential difference, and divided by current. And the current is the same through this circuit. The current is the same in every point of the conductor, and here, and here, and here, everywhere the current is the same. Why so? Because the current is the directed movement of electrical charges, and we have the law of conservation of electrical charges. The charges do not vanish, and the charges do not appear from nothing. So the number of charges that go through a unit time here at this point must be equal to the number of electric charges that move through the wire during the same time interval in any other point. So the current is the same here and here. The current through the first resistor is equal to the current through the second resistor, and certainly it equals to this current. So if we divide this fraction, if we write it in this way, we obtain that we can divide the first additive here and the second term here, and then we obtain the first term here, which is certainly due to the Ohm's law it's equal to resistor R1. And the second term in this expression, due to the Ohm's law, equals to the second resistor, to the second resistance of the resistor R2. So all this becomes R1 plus R2, and etc. If you have many resistors, then there will be many more additives in this formula. So the total resistance when you have a serial connection of resistors is equal to the sum of these resistors. And the next situation is the parallel connection of resistors. So if we have a resistance R1 and parallelly connected resistor R2, and all connected to some source of voltage, then the current which flows here will go to this point, and at this point the current will be divided into two flows, a current through resistor R1 and a current through resistor R2. So currents E1 and I1 and I2 are not, in general case, they are not equal. This will be different currents in general case because the resistors are different in general case. So in contrast to the first situation, when the current was the same through all the elements, here in this serial connection of resistors, the currents will be different. But what will be the same? The potential difference between these 2 points will be the same. The potential difference on the first resistance will be equal to the potential difference on the second resistor and will be equal to the potential difference created here on the terminals of the battery. The potential difference will be the same. And so the first potential difference will be the first resistor times current through the first resistor. And the second potential difference will be the second resistor and the current through the second resistor. And all this will be equal to, so this is certainly one potential difference equals to the other, and all this will be equal to the total potential difference and somehow related to the total resistance between these 2 points. What we have to find here in this problem is the resistance between points A and B. That is the resistance of a serial connection of resistors. So it will be equal to the total current times total resistance, and all this is certainly just the potential difference, the voltage of the battery. So we can say that the resistance of this in this circle, total resistance of this scheme, will be equal to the potential difference divided by the total current. And the potential difference, the total current, which is here, current I, is equal to the sum of currents I1 plus I2. I1 plus I2. Why so? Because of the law of conservation of electrical charges. The number of electrical charges is the same. Electric charges do not vanish and are not created. The number is the same. If you have some 1 million electrons coming to this point, then it will be divided into 2 flows, and you may have 100,000 going here and 900,000 going here. So then the currents, because the electric charges do not vanish and cannot be created, then the total current is just the sum of 2 currents. And then we may continue this formula. Electric current 1 will be equal to, from here, will be equal to total potential difference divided by R1, and electric current 2, again from here, will be given as a total potential difference of the voltage source divided by R2 due to Ohm's law. And here we may cancel U and obtain this formula 1 over R1 plus 1 over R2, and that will give us R1 times R2 divided by R1 plus R2. And in general case, if we reverse this expression, we will obtain that 1 over total resistance here from this formula equals 1 divided by equals 1 divided by R1 plus 1 divided by R2 plus etc. if we have more than two resistors connected in parallel. If more than 2 resistors are in parallel connection, then you will have similar terms here in this formula. Similar terms to calculate the total resistance in parallel connection. So if two equal resistors are here, if R1 equals R2, then the total resistance in serial connection, the total resistance will be twice the resistance of each separate resistor. And in this case, if we have equal resistors, if R1 equals R2, then the total resistance between points A and B will be as can be derived from this formula. If R1 equals R2, and here R1 equals R2, then one resistance will be cancelled, and we will obtain R1 divided by 2. So the total resistance will be R1 divided by 2. So when we connect resistors in parallel, the total resistance is in any way diminished. And if we connect resistors in series, then the total resistance is increased. That's the main idea behind these different connections of resistors. And the next issue we have to consider is the resistance of a wire and specific resistivity. So suppose we have a wire which I will draw here in a large scale to show the cross section of the wire. If the wire has cross section S, and it has length L, then how can we calculate the resistance of such wire? The resistance will certainly be proportional to L, because each section of length L will have some certain resistance, and if we increase the length of the wire, then we will have two resistors connected in series, and that means that the total resistance will be the sum of these two sections, the resistance of these two sections. So the total resistance of wire must be proportional, directly proportional to its length. That is the consequence of the serial resistance, serial connection of resistors. And also, if we increase somehow the cross section of wire, then it will be equivalent to some parallel, to attaching some parallel resistances here. So if we increase the cross section, that means that as if we applied more material here on the wire, and that will act as a parallel connection of resistors. So in this case, the total resistance of wire will be inversely proportional to the area of cross section. In this case, we may conclude that the total resistance of wire is equal to some coefficient, which I will denote by Greek letter rho, and directly proportional to the length of the wire and inversely proportional to the cross section of the wire. And this coefficient is called a specific resistivity of a material from which the wire is made. And this specific resistivity, or simply in short, a resistivity, resistivity is a characteristic constant of the material from which the wire is made. If you take a copper wire made of copper, you will have a small resistivity of copper. If you take other material like aluminum, then the specific resistivity will be higher. If you take some semiconductor material, then its specific resistivity will be many orders of magnitude larger. And also it should be noted that the resistivity of any material depends on temperature. So if you measure the resistivity of any material under room temperature, you will obtain some quantities, but if you increase the temperature, the resistivity will change. For the metals, it will increase. For semiconductors, it will decrease. So the dependence on temperature is different for different types of materials. And you should remember that this quantity is temperature dependent. And by physical meaning, what is the resistivity? What is its physical meaning? If you take L equal to 1 meter, and wire cross section also 1 meter squared, then such a lump of material will have a resistance equal to rho. So rho is the resistance of such a cube of material where this is cross section, this the side of the cube is equal to L, and this is also L, and this is L. So if you measure the resistance of such cube between two opposite faces, then this 1 cubic meter of material will produce the resistance equal to its resistivity. So in international system of units, the resistivity is the resistance of 1 cubic meter of material which has a shape of a cube. Which is not quite convenient because we never have such a large amount of substance to measure its resistivity. Usually we take very small wires, usually they have small cross section, but anyway, numerically and by the meaning, the resistivity is the resistance of such a large cube of 1 meter, the side of which is 1 meter. And another thing I wanted to discuss is a thermal effect of electric current. I promised in the beginning of this lecture, I promised to discuss the heat effect of electric current, or how the electric current is heating the conductors and resistors. And now we come to this topic. So suppose we have a resistor R attached to a battery which produces some potential difference U on its terminals, and there is an electric current flowing here, an electric current in this circuit, and there will be some potential difference on this resistor which will be equal to this one. Well, if the internal resistance of battery is 0, I take the simplest case. We have already considered the general case when the internal resistance of battery is non-zero. Now I will assume that this is 0, and we consider just what is going on in the external circuit. If a small charge delta Q goes through this resistor from point A to point B, from point A to point B, then actually this charge will be drawn through some potential difference between these 2 points, and so there will be some work performed on moving this charge, and the work will be the potential difference between points A and B times delta Q times the amount of electric charge. So this is the definition of potential difference. If there is some potential difference, if some charge goes from point A to point B, where is the potential difference between these 2 points, then some amount of work is produced. Who produces this work? An electric current and electric field which is present here, electric field. We understand that the electric field and electric current is produced by the battery, and so finally the battery will produce this work. But the battery may be far away, maybe kilometers away from this place, and so here we have only the electric field and electric current, so the electric field will produce this work when some electric charge is moved from point A to point B. And I told you that the electric current is the directed movement of electric charges. This is a verbal definition of electric current, but if we go to a strict mathematical definition of electric current, then it's defined as some charge that goes through the cross-section of the wire during some time interval delta t. And so here we may use different combinations of Ohm's law and this formula. And due to the Ohm's law, the potential difference here between points A and B is equal to the current times the resistance R. And so here we may put it like current times resistance R delta Q and also if we express delta Q from here delta Q will be equal to current times delta T, and then we may use this formula here and we obtain current times R multiplied by current. That will be the current I squared R delta T. If we divide this equation by delta T, then we will obtain delta A over delta T. What is delta A over delta T? That is the work performed during some time interval delta T. By definition, this is a power. This is a power of electric current, and the power is measured in watts. If this is measured, if the work is measured in joules and time is measured in seconds, then 1 joule produced in 1 second is 1 watt. And so if we divide by delta T, we will obtain here a power of electric current. The power of electric current will be given as I squared R. Also, this formula may be put as because current times R times resistance is voltage, then this will be current times voltage. And also you can find some other interpretations of this formula. If you take current, which is equal to U over R, U divided by R, then you will obtain here U squared over resistance, and so on. All these are possible variations of the same formula, which expresses the power released in the resistance if there is a current flowing through this resistance. So the work is produced during some time interval delta t, and so we have power, which is released here, electrical power. Where does this power go? Or where is this work converted? In what form of energy is this work converted? It's obvious that there is no other form of energy here but heat energy, internal energy of this resistor. And the resistor will be heated, and the heat energy released in this resistor will be equal to this work. Or if you take the heat energy released in a unit of time, then it will be equal to the power of electric current, and the power of electric current is given by one of these formulas. All these formulas are equivalent because all of them can be obtained from one another using the Ohm's law. And this is the power of heating, the power of heat release in this element. And when you have an electric heater, for example, which is heating the room in winter, then these formulas work certainly. You must have certain voltage and certain electric current strength in order to obtain certain wanted or desired power of electric heater. So if you want to have an electric heater of 1 kilowatt, for example, 1 kilowatt power electric heater, and the voltage is 220 volts in the circuit, then the current must be about 5 amperes, in order to obtain 1 kilowatt heating power. 5 amperes, so a fuse in your room must sustain at least 5 amperes. If the fuse is only on 5 ampere fuse, it may be broken, it may be it will be just burnt out and switch off your circuit if it's capable to carry only 5 ampere current, and you have switched on an electric heater and, for example, something else like an electric bulb, which takes about 60 watts. So if you have more than 1 kilowatt power in your room, in your house, more than 1 kilowatt power of appliances, and the fuse only for 5 amperes, then you will be unable to sustain voltage and everything will be switched off. The lights will be switched off and the voltage will be switched off due to an inadequate fuse in your house. So if you want to have some electrical appliances attached in your house of certain electrical power, then you may easily calculate the current which must be sustained in your wiring, in your circuitry, and then you may calculate what fuse you should use in your electric circuits. So this is as far as the heating energy released in any conductor. Any conductor under a voltage will conduct an electric current, and there will be a heat energy released in it. The conductor will be heated and the temperature will be increased and the heat energy will be released and radiated in the outer space. So I think we have time to solve 1 or 2 problems. And I will choose for the beginning, I will choose this problem number 460. So problem number 460. And it says, what resistance R should be used to shunt a galvanometer with an internal resistance. So we have a galvanometer that is a device to measure small currents. This is supposed to be an arrow showing the readings of the device, and its internal resistance is to be found. No, we have to find the resistance of an external shunt to this galvanometer, and the galvanometer has a resistance, internal resistance, 1 kilo ohm, and we need to reduce the sensitivity. We need to reduce the sensitivity of this device by n 50 times. We need to reduce the sensitivity by 50 times, and for this purpose we use an external shunt. What is a shunt? A shunt is an external resistance which is connected in parallel to the galvanometer. This is a shunt, and we need to find its resistance. We don't know, and the internal resistance of this device is given. It's 10 kilo ohm. Why shunting the galvanometer will reduce its sensitivity? Because if there is no shunt, all the current will go through the device, and the device will show all the current in this circuit. But if we shunt the galvanometer by parallel resistance, then some current will go through this additional resistance, and the current through the galvanometer will be smaller because a large portion of current will go here. So if the current will turn out to be smaller, then it means that the sensitivity of device becomes smaller, and we need to reduce the sensitivity by 50 times. So suppose we have some external current I0, and this is simply a resistance to the current which we know, which is 10 kilo ohm. This is the internal resistance of this device. So if the internal resistance is 10 kilo ohm and there is no external shunt, then all the current goes through the galvanometer, and it measures the whole current I0. But if we attach an external shunt, then some portion of current will go here. So what portion of current will go here through the shunt? This is easily calculated using the Ohm's law, because the current here, which is current I sub R, for example, it will be equal to what? It will be equal to the potential difference here divided by the resistance of this external shunt. And the current which will go through the galvanometer, let's designate it as I sub 1. The current I sub 1 which goes through the galvanometer will be equal to the same external voltage divided by the resistance of galvanometer. And also we know that the external current I0 equals the sum of these currents, the current IR, which goes through the shunt, plus the current I1, which goes through the galvanometer. Do we have time? And so by the statement of this problem, we have to reduce the sensitivity by 50 times reduction in sensitivity. What does it mean to reduce the sensitivity by 50 times. It means that the current which will go through the galvanometer, I1, must be 50 times less than the external current I0. So I1 must be I0 divided by n by 50. We want to reduce the sensitivity n times. So if there were no external shunt, then all the current goes through the galvanometer. But if we attach an external shunt, the current flowing through the galvanometer will be n times smaller. So what can we say in this situation? The current that goes through the shunt from here equals I0 minus I1, and I1 is expressed using I0, so this is the current I0 minus I0 divided by n. So this is I0 times 1 minus 1 divided by n. This is the current through the shunt. So we know the current through the shunt, and also we will know from the same considerations we may calculate the current. If we know the current that goes through the shunt, we may immediately use the Ohm's law and write that this current equals the external potential difference on galvanometer divided by R. And so we may find R from this formula, because we need to find resistance of this shunt, and the R will be equal to U divided by I0, and in round brackets 1 minus 1 over R. And then U can be found from here. This potential difference will be found from here, which is I1 times capital R divided by R0, 1 minus 1 over R n. And I1 divided by I0 is known. We already have written this expression. I1 divided by I0 will be 1 over n. So here we obtain 1 over n. And final answer will be capital R divided by n minus 1. If we open this round bracket, we will obtain n times 1 minus n times 1 over n minus 1. So we have found the resistance of the external shunt, which we need to use in order to decrease the sensitivity of galvanometer by 50 times, by n times. So if we know the resistance capital R, which is given to us 10 kilo ohms, 10 kilo ohm, divided by n minus 1, that is 50 minus 1, that is 49. That's about 10,000. We must divide by, well, about 50, close to 50. 10,000 divided by close to 50 will be about 200, ohm. So if we take this shunt resistance of 200 ohm, then the sensitivity of galvanometer will be reduced by 50 times. And that's the end of that lecture. That brings us to the end. And next time we will solve more complicated problems on this topic. So goodbye till next time.